know, I mean, one thing that we've done is you can think about like, if you think about like the relationship between, like kind of an analogy between like our Python code and our SQL code. Like in both cases, we started off with our Python code kind of like in one script, this like index.py, and then we broke it up to be more modular, right? Like if we have our like we could go back to like the cow lab or something like that, right? We have like this cow.py, and then we have like the barn.py, whatever it was, right? And then each of these things is responsible for kind of like a different entity. And then we said this kind of like really lined up to, our data modeling, right? How we split things up into separate tables, and we had different queries in different files, right? Like here, originally we just kind of like had this connected with an ORM. So when we have the class, we also have the table methods right underneath, right? Eventually, though, when we moved into something like DBT, right, it's that same idea, right? We cleaned up each of our tables independently, right? We had like that stage HubSpot customers.py and stage HubSpot like companies.py. We could have, like, if we weren't doing this the right way, right, we could have written the whole thing in one file. Sorry, this should be .sql. Well, you get the idea. Okay, so if we wanted to, we could have written like the whole thing just in one enormous file, but we didn't, right? It's a lot more clear if we break this up into multiple files. So that's just like one thing to think about. Another thing you may remember is like, like think about like our principles of just like classes, like why we use object orientation in the first place, right? If you have like if you just have like a pet, right? And then you say, def say hi, right? And now let's say like there are different kinds of pets. So you can say like if self dot type equals cat, right? Then it's going to be meow. Otherwise, it's going to be, let's say if it's not a cat, let's say it's a dog, wolf. Okay? But like this is to get rid of this if else statement, right? We don't like love this if else statement. What it probably is revealing is that maybe we should have two separate objects here, right? Like maybe this should be a cat class, and we just say hi, and it always prints meow, and then we have a different class for a dog, and it always prints wolf, right? So what's the equivalent in SQL? Well, like our case one statements, right? Like what that potentially could reveal is like really maybe we should have these things in two separate tables, right? Like maybe this represents separate entities, and it will clean up our code if we move this out. Okay, so right, like these same coding principles really apply. And just think about like what makes stuff hard to read, right? It's hard to navigate a file that's like 400 lines long, where it's easier if we have this broken up into smaller files. Okay, so like when you're thinking through this stuff, right, like think about like our coding principles throughout the course. That's what really applies, and we'll go through them, and you'll get the hang of it hopefully as we go along. So that's one thing I wanted to talk about. Then the next thing is just like, okay, we can get into some of the more formal topics, like an index. Okay, so by this I mean like a database index. So why do we even use this? You can imagine, let's say we have, let's say we have customers, and we have like their name and their age or something like that. Let's do that. And I know you probably would not store age in a database. You would have something like birthday, but just for this. So say we have Bob, he's like 25, Sally, she's 32, Sam, and he's 19, right? Okay, and Fred, okay, and he is, let's say he's 54. Okay, so we have these different, customers, and we have their ages. Now, if we do something like select all from customers where age equals 25, right? Think about what SQL has to do. It has to go through or Postgres, it doesn't matter what database, has to go through every individual record until it finds the match. Okay? And it doesn't know how many matches there are. So of course it's, even though it finds one here, and it has to go through each individual thing, check for equality, return the set where age equals 25. So this is called a sequential scan, right? Because you just go one by one in sequence until you find a match. So a different way of doing this, kind of like that we learned about, right, is to hash this data, right? To like put this through a kind of formula that says, okay, 25 actually equals this location, right? Like location number, I don't know, 67. And 32 is going to put it through a function and it gives you back, this other location. So maybe it's like 74. So basically, at this point, what we do is we look for, you can say, okay, we look for the people that match to be 25, and each of them could be indexed and have maybe the 25 and the ID corresponding with it. So this 67 would have like an ID of 1 next to it. So it's like we're looking for 25, we're going to go to this location, there we see the matching customer ID, something like that, right? So this is just a hashing function, and this is one way to perform an index. Right. What's nice about it is like it will work something on a string as well. Right. You take this string of letters, you pass it through a function, and let's say the function is assign a value to each letter. So B is 2, and let's say O is the 10th letter, and then the last B is 2 again. So this would be 14. So when it sees Bob, it will look for 14. Right. It's not a very good hashing function. We've talked about why before, but like that's the idea. Just go to 14. See that this ID is located there, and now we no longer have to go one by one by one. All right, so that is one way that you can do an index. Index can be hashed. Okay, just a hashing function where we have an input, it gives us an output, and then when we look for Bob, we say, okay, what does Bob correspond to with our function? It corresponds to 14, so we go to location 14 and see what's there. All right, so that's one technique, one way that indexes kind of operate under the hood. The other way, they actually the more common way, the way that Postgres will do this by default, is with a binary tree. So let's talk about why just using it seems great, using a hashing function to me, because we just have to go one spot. What could be better than that? So the issue with it is, what if I want to say, find all the people younger than, let's say, 40, okay? Now we kind of have it. Now we can't really use our hashing function anymore. Right? We could maybe go to every single number and find the corresponding value and then be like, oh, okay, 25, we took care of this guy, 26, right? But essentially, we're not saving any time anymore. We're not just able to go to one spot and do that. It feels more like a sequential scan to me. It feels more like we kind of have to try them all. So what can we do instead of this? You can organize the data using what's called a binary tree, okay? Like a binary search tree. So the way that works is, let's say we start with a given number, 32, okay? And then everything to the left is going to be, let's say left is going to be lower. That's an arrow. And then to the right is going to be higher, okay? So 32, everything to the left should be lower. So that gives me 25 here. Okay. Actually, I'll do this even better. I'll put 19 here. 19 is lower. And then 25, am I doing this right? 32. I think actually the way we have to do this, is everything to the left will be lower, so that's fine. 19 will be lower. We can look at something like 54, and I think this kind of can go here for higher. I may have to look this up again though. All right. So now if I want to see what are the numbers higher than 32, right? It would only be stuff that goes down this path. All right. So the idea is, let's see if we can do this for another number. So 25. Okay, so 25 is lower than 32. So what we should do is go to the left, we get to 19, and the only way now that 25 could be any higher is on a right branch. Okay? So what's nice about this is this will, like, ideally with a binary search tree, each of these, I think I'm messing it up, each of these will have only two nodes to it. So your depth actually will not be too high. All right, it's actually going to be what's called like log of n. So your depth is not going to be too high, and based on whether or not you're trying to look for something higher or lower, you can then see the value that's located there. I'm going to re-explain this later, but this is the other technique, and the main benefit of this is it's an easier way to see like what's located by value, essentially to sort these values. Right, because the Bob with age 25, we don't have to look through every single location. We can just kind of say like, okay, 32 needs to be lower than that. So let's go to the left, 19. Now we need something higher than that. Go to the right, 25. Okay, and we found it. If we don't find it, right, then it's not there. So this is another way of indexing, is to use a binary tree, right? And the idea here is that this data is sorted, right? It is sorted. What's the cost of it? Well, the cost is like as new data comes in, you'll have to what's called rebalancing the tree. You'll have to like kind of switch some of these values around. All right, so that's another technique of indexing, is doing a binary tree. And like I said, I'll try to review this and give you guys a better explanation. But that's the idea. All right, so that's indexing. Indexing, there's really like these two techniques. One is hashing, right, where you just like give in a value, you put it past their function, it gives an output. The other way is like a binary search tree, all right. And the benefit of the binary search tree is, well, it's ordered, right? It's still organized, but it has some order to it, and so we can do something like select all from customers where age is say greater or less than 25, and it makes it faster to perform. Okay, so that's the main stuff I wanted to talk about. The other stuff to just think about is joins. Let me show you this. Maybe I need to give me 1 second. I may just have to make it should be public. Okay. So for joins, the main technique, the way that joins works, is called like a sort and merge technique. So the way that this works is, say we have this is our primary key, customers.id or .customer ID. And now this is our foreign key, so orders, and orders purchased by a customer. Okay? In order to like join up, right, to say, okay, if I join customers.customer ID equals orders.customer ID, what it does is it performs a sort and merge. So the sort part is, you can see these records are already sorted by what's supposed to equal the other thing by the customer ID in each case. Okay, if they're not, it will need to perform that. But because generally Postgres will index the primary and foreign keys, generally they're already like in that B tree that we just talked about. So they generally already are in a good way to like see, okay, what comes next? What is there a 2 after the 1, etc. Okay, so the first step is sorting. This is in sorted order. This is in sorted order. Then it starts with whatever's to the left. So if we do select all from customers, join orders, right? Customers is to the left. And then we go to kind of the first, the first foreign, in this case, primary key, first primary key, and see, is there a match? Okay, because it's sorted, here we have a 1, so we have a match here. And then we go to the next one, 2, right? Is there a match? Well, we just finished with 1, and we already got to 4 here. So because this is sorted, we don't have to look any harder, right? We know that 4 is greater than 2. There is no 2s here, okay? So that is, the primary way that Postgres is going to perform a join. These joins are still costly, okay? So you should try to optimize them. How do you optimize them? One way is you can simply, what you would think, we can simply join fewer tables together. So instead of joining every table, sometimes that's simply not necessary. Another way that we can do that, another thing that we can do to reduce the data is just join fewer, not the entire data set. So for example, if for customers, we only need customers who purchased in the last week or something like that, or let's say customers below the age of 25, right? Then obviously we're joining on fewer components of the data, right? So that's a second way. Fewer tables, fewer rows, right? Another thing to do is make sure you're joining on a column that's indexed. Like I said, if it's a primary foreign key, Postgres will do that automatically for you. However, if you say join on first name, right, which I think we did do in our DBT lessons, right, there we had to do that. It seemed like, we could have created an index on name if this is something we really needed to be time efficient. But it's also just something to be aware of, to know that, okay, ideally we're joining on an indexed column. And then the other thing I see, this is kind of to try to have the table that's smaller over to the left. I don't think it really matters with this technique, with the sort and merge, but there are other ways that Postgres can do a merge if it doesn't do it this way. And in those cases, having this table with fewer records to the left can help. The other way that Postgres does a merge is with a hash join. The hash join, it literally will, say, take this ID, each one of these values, pass it through a hash function, right? And in that case, the whole left side of the table has to be hashed and stored in memory. So having a smaller hash table here will make it more efficient. So, if you can, the other technique is just if you can have the left table smaller, be the smaller one, that can help as well. All right, but the main things is, just be cognizant. Don't join every table if you don't need to. Use fewer rows if you can, right? And make sure that you're joining, or try to at least join on something that's indexed, okay? Right, and just in general, integers are going to be easier to join on than strings, because a string you have to check every character, right? Integers are going to be easier. All right, that's the main stuff. Then there's a bunch of other little tips and tricks with SQL that I'll just let you read through. But one thing I'd say about going through this is, this will give you some intuition as to how Postgres is doing this, but hopefully you start thinking about how does Postgres, how does it do a case one statement? Think about what needs to occur for it to check equality there, right? And how long do you think something like that will take, right? We talk about how distinct works in this. Okay, so hopefully this will just give you some intuition, and then obviously you can always Google, to see okay, how does a case when compare to just say performing another operation, right? You can actually trade off case one statements for select statements in certain cases. So anyway, those are things to start thinking about. All right, I'm gonna try to do a better job with the binary tree stuff. I'll look at that again, but I think hopefully you get the idea with it. And then the reading also